This presentation is Module 7 of Chem for Bio at Northern Virginia Community College, Annandale campus. The topic of Module 7 is solvents and solutions. It's been broken into two parts. This is part 1, where we concentrate on solutions where water is the solvent and the definitions necessary, the vocabulary necessary to understand these solutions. So, are you thirsty? Would you like a cool sweetened drink, maybe some fruit punch, or perhaps a warm cup of tea or coffee sweetened with a little sugar or honey? From a scientific point of view, all of these substances are what are known as solutions. By definition, a solution is a homogeneous mixture of at least one solute and one solvent. The solute is defined as the substance being dissolved, and the solvent is the substance doing the dissolving. The solvent is almost always there in a larger amount than the solute, but it's not mandatory. So what's a homogeneous mixture? If a solution is homogeneous, if a mixture is homogeneous, it has a uniform appearance, it looks to be only one physical phase, and the composition is uniform. That is, the concentration is consistent throughout the solution. So, when you make Kool-Aid, you dissolve the drink mix packet, which is one of the two solutes, and you dissolve the sugar, which is the other solute, into the water solvent. You mix it until it is totally dissolved, and you have a homogeneous mixture, or a solution. When water is the solvent, we say it is an aqueous solution. So, what does water like to dissolve? It should be no surprise. Water wants to dissolve other polar molecules and ionic compounds. Solutes can vary in their physical state and in their behavior. Sucrose, which is just table sugar, dissolves in water as molecules. Sucrose is a covalent compound. It exists in molecule form. So as the solute, the attractive forces between the sugar molecules are broken, and they're essentially replaced by attractive forces between the sugar molecules and the water molecules. We say that sugar is a non-electrolyte because when the molecules dissolve, they do not break apart. The molecules just separate from one another, but the molecule itself does not break apart into charged ions. Consequently, the solution that's formed cannot conduct electricity because there are no charged particles floating around in the solution. You can contrast this with when you dissolve a salt, such as sodium chloride. When sodium chloride is dissolved in water, not only does it dissolve, but it dissociates. That is, the cations and anions, the sodium plus cations and the chloride minus anions, split apart. And they are both surrounded by water molecules. So you have these charged ions isolated from one another by the water molecules, by the solvent. And they are isolated charged particles. Consequently, we say that sodium chloride is an electrolyte because when it is dissolved in water, those ions are capable of conducting electricity. Just so you know, when these ions are separated from one another and the waters surround them in this spherical arrangement, this is called the hydration shell. It is simply a sphere of water molecules that surround each ion and are attracted to each ion. So again, to recap, a solution is made of very small particles. Both the solute and the solvent are relatively small particles. The particles do not settle to the bottom of the container, nor can they be separated by filters or semipermeable membranes. In other words, you cannot easily separate the solute from the solvent once the solution has formed. We contrast this with colloids. Again, in a colloid, we're still talking about water as the solvent, so it's still aqueous, but the solute molecules are larger molecules, or small groups even of molecules and ions. The particles, the solute particles, still don't settle to the bottom of the container, but they still can't be separated by filters, but they can be separated by a semipermeable membrane. A great example of a colloid is homogenized milk. Its specific term is emulsion because both the solute and the solvent are liquids. Contrast that with a suspension. In a suspension, the solute molecules are actually very large particles relative to the water molecules. They can be aggregates of molecules. And over time, those solute particles will indeed settle to the bottom of the container, and they will separate from the solvent. Classic examples are things like snow globes, which is what you are seeing in the figure. Those little silvery particles are temporarily suspended in the water solvent, but they will fall and settle to the bottom over time. Anything that says shake well before using is in fact a suspension. So calamine lotions, any antibiotic that comes in a suspension form that you have to shake well before using, those are suspensions. So now we're back to why does water dissolve things? Not too surprisingly, it has to do with water's polarity, its ability to attract other polar substances, other ionic substances, its hydrogen bonding ability. If a solute is attracted to the water molecules, in biology we say that it is hydrophilic. Hydro being water, philic being loving. So hydrophilic, water-loving substances. Ordinarily, those are other polar molecules or ions. They interact readily with the water. The attractive forces between those solute particles and the water are relatively strong. So we're talking salts, strong acids and bases, even weak acids and bases. Any molecule that can hydrogen bond with the water, water-loving, hydrophilic. We contrast this with hydrophobic substances, water-hating or water-fearing substances. They are ordinarily nonpolar molecules, nonpolar compounds or elements, and they don't interact readily with water. They, in fact, physically separate. So if you have a mixture of oil and water, that is not a homogeneous mixture. That is not a solution. The water molecules are not attracted to the oil molecules. The oil molecules are less dense than the water molecules, and the oil will separate and float on the surface of the water. Oil is hydrophobic. Now, we can have substances, solutes as you wish, that are both water-loving and water-hating. In other words, one end of it is hydrophilic, one end of it is hydrophobic. We call them amphipathic substances. Ampha for both, pathic for suffering. They will suffer both. So the hydrophilic regions of this molecule, and they're usually pretty large molecules at this point, The hydrophilic regions will interact with the water. The hydrophobic regions will separate from the water. There are all kinds of examples of these amphipathic substances in biology. One good example, phospholipids. The phospholipids organize themselves into bilayers, where the water-hating, the hydrophobic end of the phospholipid interacts with other phospholipid ends, and we actually call them hydrophobic tails, while the hydrophilic, the water-loving end of the phospholipid, points out towards the water in the extracellular space.